Okay, another useful quantity that comes into play when we talk about circular motion is period, which is the time it takes an object to move all the way around a circle. So suppose we have this circle, has some radius, and we have an object with some tangential velocity, vt. Then the period is going to be the time it takes to go all the way around and get back to the beginning. So it depends on the velocity. So the faster it goes, the less time it will take, the shorter the period. And we know that the tangential velocity times time is equal to the arc length. That's how far it goes along the arc. So it carves out this little piece like there. So if I know the time it takes, I can tell you how far it went. Well, we want to know all the way around the circle. And if I go all the way around the circle, that's called the circumference. And so the tangential velocity times the big T, so that's period, is equal to the circumference of the circle. And then we have the velocity tangential times the period. We use big T, don't get confused with, it's also temperature, it's also tension, but you got to know the context in which we're talking. The circumference of a circle is 2 pi times the radius. And then if we move that over, we get the period is going to be 2 pi r divided by the velocity, tangential. And so that's the period for a object moving in circular motion, uniform circular motion. 2 pi r, or the circumference, divided by the time it takes to go all the way around. And then we can, we can use that maybe for centripetal acceleration, which is v squared over r. So we see that v squared, well, if I rearrange this, I get back to this. V squared, v is going to be 2 pi r divided by the period. So that will tell me, like, if I go all the way around, how long did it take? That will tell me the velocity. So if I take this and plug it in there, I get AC is equal to 2 pi r over t. And then all of that is squared divided by r. Simplify. 2 squared is 4. You get pi squared. And then r squared, but there's an r on the bottom which cancels one of those. So you get times r divided by t. So we get this new definition. So this would be the acceleration in terms of the radius and the period. So if I know the time and the r instead of the velocity. So anyway, it's just a different way, but this is not given to you. You need to know how we come from period and get to there. So let's see, how could we apply it? Let's think about the Earth. So we're talking about the Earth, and let's talk about the equator. So it's a sphere. So if you're standing here at the equator, what's your centripetal acceleration as this goes around? So we know that the radius of the Earth at the equator, well, remember that it's spinning like so about its axis of rotation. So it's going this way. And so we want to know what's the acceleration. The radius of the Earth at the equator is 6,400 kilometers. And we also know the period. How long does it take somebody to go all the way around the Earth? Well, that's 24 hours. So we have to convert this stuff, but we can see that the acceleration, the centripetal acceleration, would be 4 pi squared r over the period. So we get 4 pi squared times the radius, 6,400 times 10 to the third meters over 24 hours is 1 hour is 3,600 seconds. So divided by 24 times 3,600, and that would be seconds. So we get a centripetal acceleration of 0.034 meters per second squared. All right, so this has implications. So imagine I'm going to put this upright, so we're going to look at him standing here on the ground. So there's two accelerations. There's the acceleration due to gravity, which is g, pulling down, but there's also this centripetal acceleration, pulling down. So the acceleration of an object is actually g plus this little tiny amount at the equator. So that would be 9.8 plus 0.034, which would be 9.834. So this little piece right here is what's added on just by the fact that we're moving in a circle. So we get a little bit more weight. You'll weigh a little bit more up here where you have a greater, well, we should talk about that. So if you're moving around in a circle at a higher latitude, you can see the radius is much smaller, but the velocity, we have to move the same. We have the same period, so you get a smaller radius with the same period. So we end up with less centripetal acceleration. Sorry, I had that backwards. We end up with smaller acceleration up here because we'll do this when we do rotation, but anyway, you end up with less centripetal acceleration up here. So you'll weigh less up here than you will down here. So you weigh more at the equator, and that's because of this, but it's negligible. We can ignore it. Anyway, that's period.